All right, so in this video we're going to move on to, well, more general, more complicated movement of particles. So far we've only been discussing in detail the motion of particles that are moving along a straight line, and why we started there because a lot of real applications, a lot of what we go to analyze can be completely described by particles moving along a straight line, and it's convenient because then we can just use scalar quantities. S is our coordinate for position along that one-dimensional line. Velocity and acceleration, not vectors here, they're scalars. The direction is all coming in this chosen unit vector E hat, which is just the direction that the motion is along. More generally though, particles continually are curving in space, right? Or their paths at least fill up space, and can go in any of the dimensions. And so we'll need to describe that type of a motion, the more general motion, in terms of vectors for position, velocity, and acceleration. To do this, we are going to study, we're going to start with Cartesian, right, what we're familiar with, but we'll also talk about two other types of coordinate systems. The second one being the natural coordinate system. So it means we actually choose the coordinates to be along the direction, actually that's tangent, and completely perpendicular to the motion direction, and we call it natural because it's really natural. It's just say, well, one of our coordinates is always in the direction of motion. Where this gets hard, and where it just gets more complicated, is that the actual coordinates are changing in time, right? So as particles move, our actual coordinate system kind of shifts and rotates itself. And then the third one will be the polar cylindrical coordinate systems. Those are actually both the exact same. Polar coordinates is just two-dimension, where you just have a radius and a angle. And cylindrical is then extending that to 3 dimensions with a z-coordinate, just like the same z-coordinate as you have for Cartesian. So it's a different way to express x and y for things that are more naturally circular in their nature. So but we'll have full lectures on this. This lecture is going to be devoted to curvilinear motion with Cartesian coordinates, and then we'll talk about these others. Now these, right, before we jump into them, right, just remember, like, these are choices. These are choices for analysis, right? It's not, again, the universe doesn't impose that certain systems are Cartesian in their nature or natural or polar in the nature, right? That comes from our choice as the engineer, as the mathematician, as the physicist, whatever you want to say. As the person, the thing doing the analyzing, we then choose we make a choice for a convenient choice for a coordinate system that will then lead to simpler analysis down the road. And oftentimes there's pros and cons to making that choice, and those need to be weighed going into a problem. Okay, so let's jump into the first one here, which is Cartesian. This is 13.4 in the book. Okay, curvilinear motion, Cartesian. All right, so let's start here with a diagram of a path, and maybe it's not fair to even put the coordinate system on there yet. I mean, maybe even pretend that's not there yet. We just have this particle moving through 3-dimensional space, and the best I can do is put it on 2 dimensions on my 2-dimensional page. But and then that's the particle kind of sweeping through this path through time, right? Then we choose to analyze it, represent it with, well, we need 3 coordinates for 3-dimensional space, and it really comes down to it being Cartesian has this nature to it, right? This, to the right, up, and then kind of z would be sort of out at us as we're looking at it. And then the origin O really sets where the 0 position point is in all of those coordinate directions. Okay, so as we've seen back in one of our initial lectures here, right? The position to get to the position vector to get to that point P, the particle position at that time instant, is from the origin to P, right? So position vector. So in a way, some of this should feel a little bit like review from that previous lecture, but we're going to put things into the right terminology, into the right place so that we can extend these to more complicated coordinate systems. So point B is then relative to the origin of our Cartesian coordinate system, right? This is what we mean by a Cartesian coordinate system, right? Point O kind of defines, maybe here, that O point defines the Cartesian coordinate system. Okay, that position vector, function of time, is then, how does its x position change in time? Okay, and that is in, well, maybe at this point we need to even put in, I can't, I have an I hat there. What is that? Well, what we do is, this is, the hat means it's a unit vector. Again, that means its magnitude is 1. And come back, we don't need to put them here at the origin, but maybe it's a convenient place to put it. Right, these just give directions for the, these individual coordinate directions. Okay, so let's get this all the way down here, this definition, and then we can talk about them. Okay, right, so what we're saying here is that the position vector, which fully describes where P is in three-dimensional space, is given by a coordinate, a scalar quantity x that changes in time, but what doesn't change in time is the unit vector, meaning that's how much we've gone from, that's x of t is how much we've gone in the I hat direction to get to this point. So it'd just be, this little bit here. In fact, let's try this. Okay, so let's say that the point, let me just put some perspective on this. So let's follow this down. Okay, there. I'm going to put 3 dotted, maybe I need to dash them for them to really show up well. Okay, so at this current instant in time, this length here is x of t, and that's how far we've gone from the origin only in the I hat direction. So we're kind of projecting the r vector here into the I hat direction, right? Then this would be this is actually our z of t, and then this vertical here, as we've drawn it, is y of t, right? So how much have they been projected in each of their directions, where I hat, j hat, and k hat are the unit vectors? Okay, great. So this is our time-dependent position vector, since P moves along a curved, for this general curvilinear path. Okay. Now let's be really careful here about the, again, I know we have experience with our unit vectors, we have experience with representing positions with vectors, hopefully. But in order to prepare us for the more complicated ones to come, especially the natural coordinates, let's be really careful here, because what's going to change later on is that these unit vectors, when we go to other coordinate systems, are actually going to be also functions of time. Here they're not. These are just fixed. We're fixing our coordinate system to be in time. It's not moving around. So what's always true of unit vectors is they have magnitude 1. So they don't tell anything about the coordinate directions, like how far away we are. They just give the directions, and they are responsible completely for the directions. The directions don't come at all in x, y, and z, those values, right? Those are just the coefficients on those directions. Okay, these are then directed along the coordinate directions, or the axes, x, y, and z, and they are constant in time. Okay, these make up the base vectors. These are the base vectors of the Cartesian coordinate system. So what we mean by that is any position vector can be decomposed, and is conveniently decomposed, into coefficients on these I, j, and k. Right? So if you can write, if any position right, vector in three-dimensional space, which just saying that alone, R alone, doesn't assume that it's Cartesian. Could be anything, any of the other ones as we go along here, right? But it's just from, from some origin to some point in space. Right, so this position vector, if you can go to any, space, any position in three-dimensional space and decompose it into an x, a y, and a z that are in the directions of I hat, j hat, and k hat, that's by definition are the base vectors, I hat, j hat, and k hat. Okay. All right, so I need a new page here. It's not going to go away forever, but what I mean is we'll refer back to this diagram when we need it. So keep that one close by. Now let's move on to, we've looked at the picture and kind of described what the velocity vector, or so what the position vector is. Let's then move on to the velocity vector. Okay. So by definition, velocity vector is dr dt, which, let's write it like this, right? R hat, or the R vector is x I hat plus y j hat plus z k hat. And this is where it's key, right? Not always going to be the case. Oops, did I go too far? Okay, not always been the case, but we can make this nice and easy since these three do not vary in time. No matter where our position is, no matter where particle P moves to, don't vary in time. I hat, j hat, and k hat are these fixed positional vectors, okay? So we can pull them out of all those time derivatives, and we have a nice convenient way to write dx dt I hat plus dy dt j hat plus dz dt k hat. And now it's starting to look like, well, this looks a lot like the position vector where it's just some coefficient out front multiplying those directions in our base vectors, right? So this is the x component of the velocity vector. This is the y component and z component of the velocity vector. Okay, so these are our vector components and how we define them. Okay, such that velocity is vx I hat plus vy j hat plus vz k hat. All right, so just being thorough here, okay? So now we'll do something very, 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 very similar for the acceleration vector in Cartesian, which is definition, this is general so far, acceleration equals dv dt. Now since we're in a Cartesian, now we can say, well, this is just dvx dt I hat. Again, we can take the I hat out of the derivative. dvy dt j hat plus dvz dt k hat, where this then is the coefficient, and so that gives you the x component of acceleration, the y component, and z component of acceleration. So these are now the vector components for acceleration. Great. And again, for completeness, with this definition, we can now express the acceleration vector as its components multiplied by the base vectors to our coordinate system. Cool. Okay. Now, just one like note here, because of how easy this was to go from position to velocity to acceleration, oftentimes what we do is, if our 3D motion, again, we're in kinematics, we're just describing motion, how does position, velocity, and acceleration compare, without talking about what's causing the acceleration, like the forces in the system. We will get to that, right? Note, if the 3D motion can be decomposed, decoupled, we often just solve three independent, well, they might relate to one another, but they're not coupled together, kinematics problems. So let's work through a general example, which is, well, maybe the most classic example, one that I'm sure you've seen, which is projectile motion. So a classic example here is projectile motion. So what we mean by that is, well, we're not going to use any numbers here, but let's work through a particular commonly seen scenario where maybe we have somebody standing up on this hill. Maybe they take, there's like a ball or something, and they kick it upward, and it inevitably hits the ground because there's gravity involved. Again, we don't care what's causing this, but we just know that it's there. We do care what's... Right, there's some direction of g there. Okay, so what we mean by decoupling the system now is if we'll look at the x and the y directions separately. And by the way, z would be coming right out at us. And so that, trivially, doesn't have any motion in it whatsoever because there's no, forcing, there's no acceleration into and out of the page, and there wasn't any kick in that direction. It's all kind of living inside the page here, right? So we've decoupled the z motion, which is just trivially nothing, right? Okay, so in projectile motion, there's a few assumptions we make. Okay, one is constant gravity. If we have to say that g depends on the height, so as your y changes, the actual value of g changes, things get more complicated. But if we're near, near Earth's surface, this is an okay assumption. Also, this acceleration is only in the vertical direction for true projectile motion, right? You could add another acceleration in the horizontal or even more in the vertical, and it would be an extension of projectile motion. We neglect drag, right? So we're getting at kind of the forces involved. Gravity is the force involved, so it's constant. Neglect drag, so as the ball is in the air, it's not like feeling any drag from the air. And we ignore the curvature of the Earth. And really, writing down these assumptions means that, hey, if you get to a problem where you can't make one of these assumptions, don't then apply our final results that we get here, right? That would be a mistake. So in the end, these assumptions, what they allow us to say is that the acceleration in x and z, which is that coordinate coming out at us, is 0, and the acceleration in the y direction is just minus g. Okay, so now let's take let's just be done with the z direction. So I'll just make one more statement over here. As drawn, so that was a convenient choice to draw the xy plane where all the motion is, meaning we haven't like taken some tilted direction where we'd have to consider the x and z axis here. But we chose this smartly so that we have no motion in z, and we don't really even, it's trivial that there's no velocity in z, there's no change in position in z into the in and out of the page direction because there's no acceleration in z, right? Okay, but what we do have is a motion in x, and that comes from this initial kick. Right? You kick the ball, and there's some initial velocity there. So we can decompose that. Well, let's write it like an initial v naught, and that has an initial v naught x and an initial v naught y, all related to some angle of the kick. Yeah. Later on, maybe at the highest point is something we often want to analyze. Up here at the highest point, there is some velocity. Well, that velocity is always tangent to the motion, right? So the v up here is equal to vx only, right? There's only an x component. So in terms of just the scalars involved, we can say v equals v of x just the x component, right? In general, maybe like later on, even later on in time, right, there's some tangent there. Draw a longer vector because that's higher. In fact, I know, right? We know what happens here, right? This initial kick in the x direction, there's nothing to change that in time, right? There's no acceleration in the x direction, so that distance should always be the same. So I kind of underdrew it here. I should have drawn my vector even further there to make sure that this horizontal distance is always the same, right? So maybe this is like, to draw it most generally, this is our velocity vector as a function of time. When we get to this x of t, y of t position, right? That's kind of right there. And maybe even better than drawing our coordinate system out here, maybe we call this is actually probably the best thing to do. This is our I hat direction, j hat direction, and k hat direction, where the actual coordinates affix at a particular point, which we'll put right here. Right, so this is actually y, and if I could sneak it in there, there's x. Yeah? Okay, because this is the origin of our coordinate system. That's better. I like that. Okay. When we get down to this general point here, then this is our Vx as a function of time, which we want to analyze. And this is our Vy as a function of time that we'd like to analyze. Okay, I think we have everything that we, the diagram is complete. Maybe if there's any trouble in seeing anything there, zoom in for just a second, take a screenshot or whatever you need to do, and we'll zoom back out, zoom a tiny bit back in. Okay. So let's go to now relate these. The goal would be like, can we write this in terms of maybe just the known quantity as how much oomph I've given, how much kick I've given, how much initial velocity I've given. So we don't know the force involved in the kick. We're not there yet. We're kinematics. So we just know the initial velocity I kicked it with and the angle at which the kick happened. Okay, so that's the case. Well, we know that our kinematic relationship, all right, using our kinematics, Vx is just going to be v naught x plus ax of t. All right, so what we're doing here is the x direction kinematics. This is perpendicular to gravity. Okay. This is completely general here, so but there's no acceleration, right? That's 0. So our Vx as a function of time is just v naught x, which is v naught cosine theta, as we see this triangle right here, right? If this is the thing that's specified, the magnitude of the initial velocity, we just need to take cosine of theta, multiply that out, right? That's because cosine of theta, SOHCA TOA, right? Adjacent over opposite. Solve that for v naught x. Okay? That's good. And if you look there, right, that is completely that's completely independent of actual time, right? So you see, like, we wrote this as Vx as a function of time, but there's no time over here. Okay, the angle was the initial angle that we kicked it with. V naught was the initial velocity we kicked it with. This is just, that's why that horizontal distance should have remained the same the whole time. We can then get to the position x of t, right? The x position. That's this, like, I know, so at some later time, what is my x position, right? Well, that is just x naught plus v naught x t plus 1/2 ax t squared, right? Oh, and by the way, I should say here, right, this is a constant acceleration case, right? If we see here. In fact, both of these are constant acceleration. So here, maybe. As soon as we knew this, we can then apply our constant acceleration kinematic relationships in 3 independent coordinate directions. All right, You just realize it might feel like we're pulling these relationships out of nowhere. Remember, we've already gone through, if it's a constant acceleration, what do our kinematic relations look like? And we're just applying that here, okay? In fact, it gets even easier because acceleration is identically 0. We also started our kick at the 0 x point. There's no, this is still 0, okay? And so our x of t is just v naught x, which is v naught cosine theta times time. Great. Now let's do the y direction too, right? This is only one direction. Okay, in the y direction, still constant. So this is the direction of gravity. We still have a constant acceleration, yeah, but it's not 0. So a little bit more complicated, but constant. So we can still use this general kinematic relationships, okay, but we just don't cross that out, right? So Vy of t is then v naught sine theta, okay, and then Ay is minus g, our acceleration in the y direction. And those are all things specified, right? We specify the kick angle, and we specify the initial velocity magnitude. We know what g is, and then for any given time we can get the velocity in the y direction. And so then our y position as a function of time, we go to our general form for constant acceleration, kinematic relations. Okay, one thing we can cancel out is just we assume we start at the, we put our origin. That's why I was careful to put our origin right there. So basically we can cancel those out. So then our y of t, any time, right, is just going to be v naught y. There's v naught sine theta times time. That's the multiplication, minus 1/2 g t squared. Great. And that's it, right? So working through in a general way without any numbers, we now have the velocity and position for this projectile motion, classic example of using the Cartesian coordinate system. All right, so let's now we'll do an example that actually has numbers, more of a full example here, something like you'd see similar in working through a homework problem. Okay, so let's say what we're trying to model here with this kinematic, so description of motion here is like, let's say we're going to throw a ball to a friend who's running, and maybe you're up on a ledge of some kind, or you're sitting up in a window and you're trying to hit a moving car with a snowball. And looking at the velocities I have here, well, I guess if somebody's running really fast, 10 feet per second makes a lot of sense. So let's just get the picture down here first. Here's our x direction, here's our y direction. B is, well, in my example I say that would be you, the person doing the throwing. A is down here at the origin. Okay, let's say they're separated by 100 feet. And let's just have like a list of what's given to us here, right? So A travels to the right at 10 feet per second with acceleration of 2 feet per second squared. So this is V, okay, let's be careful with this. This is VA initial, so VA naught, initial VA, and that's 10 feet per second. And, oh, this is important here. this is a frictionless surface, so it's just sliding here. Doesn't that's why it's like running. And so as the person runs, they don't lose any energy as they run along the floor, let's say. Or it's just like a particle that's like sliding. It doesn't go any further than this. Okay. So it just moves along there, acceleration to the right at 2 feet per second squared. But there is G, right? There is gravity because there's like a ball being thrown that's affecting all up here. Okay, great. So let's say that VB naught, what we're trying to find here is what this is. So find VB naught that's required to have B strike A as it's running along. So you want to throw the ball and have them be able to catch it. So hit them right in stride or whatever. Okay, now this could come in. There's a magnitude here and a direction. So the direction is specified in the problem statement. Okay, so there is and it's specified by a 3, 4, 5 triangle. Okay, so that specifies the direction. You could work through the fact that it's a 3, 4, 5 triangle, what the angle is, but we don't specify. It's not like 5 is VB naught. Okay, we're looking for the magnitude of that vector that has a slope of negative 3/4. Okay. All right, I think that's it. So the picture looks something like this, right? So it'll be shot off there, thrown there. It will then have a parabolic shape to it as it falls, and we want to have A and B meet each other at that point as A moves to the right and B kind of moves down and to the right. Okay, so let's analyze particle A, right? So we need to then be able to have expressions for both the position, the x position of A and the x position of B, have them meet at the same point when B's y position hits 0, right? That's basically the structure of this. Can we get an expression for XA? Can we get an expression for XB? And then set them equal to each other at the point when y of B hits 0. Okay? So start with particle A. We need to get the x position, which is XA of t. Okay, we make some comments about what we know. We know the acceleration of A in the x direction is always 2 feet per second squared. That's specified in the problem statement. We know that the initial velocity in the x direction, okay, so lots of subscripts there, is 10 feet per second, right? So this is the velocity of A, just specifying for particle A. Its initial velocity, so only at time 0, and only the x direction is 10 feet per second, or 10 feet per second. And then its x position initial is at the origin, so 0 feet. Okay. Note here that it's also specified in the problem statement that there is no y movement for A. Okay. And that's because y A starts at 0. Its velocity initial is also 0, right? It doesn't have any up or down, and it has no acceleration in the y direction, specified also in the problem statement by this being a frictionless surface. Just saying basically, and also in the words, right? It accelerates to the right at 2 feet per second squared. It doesn't have any acceleration down, right? Physically, it's just because it's on the surface. Okay, so we don't need to do any work over here in the y direction for A. We only need to do it in the x direction for A. Okay, now this is constant acceleration, right? Constant acceleration. So we can use our constant acceleration kinematics relationship. XA as a function of time is that's an equal sign, is equal to XA initial plus VA initial times time plus 1/2 of the that constant acceleration in the x times t squared. Okay, I don't like my equal sign not being right in the center. Problem of using the pens. Okay, so only thing we can cancel, well, that starts at 0. So XA of t is, that's 10. and a is acceleration of a in the x direction is 2 divided by 2, so just t squared. Okay, now right, so let's, I already verbalized this, but let's like write down, so we have it down on the page, what we're actually doing, right? T in this case is a variable. T is a variable. What we are doing, we are seeking, what we'd like to do is seek a VB naught, the initial VB, the magnitude of the initial velocity vector for the B particle, such that A and B travel to the same xy point, so xy location, at some time t star. And it's an important time, right? So you give it a t star. We don't know what it is yet, but it's at some point, right? So what we're saying here is that, so that is, i.e., it's like some Latin thing for that is, we're seeking to have xa t star equal xb at t star, and at that exact same time ya equals yb, which have to equal 0, because y of a is always 0. They're going to meet on that surface somewhere, right? So I think having it down in terms of the mathematical relations really hones in on like what we're actually trying to do here, right? Okay. So that allows us to now move on to particle B. Excuse me. Particle B. We'll come back to this, right? Here we now relate x position, that's xb as a function of time, to the unknown VB naught, right? You can see how that, if we can get an expression for xb through this setting, right? Set those two equal to each other. This relationship will set what time we're at if we can get an expression for this, right? We get an expression for that, we can solve for what time it gets us to hit the surface. That might depend on VB naught, right? And then relate xb to VB naught. Set that equal to up here. Those should be enough relationships to be able to solve for what this is to what VB naught is to satisfy these conditions, right? And if that's not like clear, if that just doesn't jump out to you as like that's the thing, just start working through the relationships, and at some point you just count up, right? Here is like one equation for two unknowns, right? We don't really know what xa is for the collision point, and we don't know that important time either, right? So that's two equations. We just got to keep building relationships and seeing if it adds more unknowns. And sometimes, you'll work through some analysis and it didn't really help you out at all. You didn't get any closer. Okay, but this is definitely one relationship that we will use. But we do need more. Okay. So we'll do something very similar to what we did for the position A here in the x direction. We'll write down all the things that we know about in the particle B in the x direction. So we know it doesn't accelerate, right? Like A did, because it's in this is projectile motion, by the way, right? So particle B is a projectile. So that the relationships that we just derived earlier we can now apply, and the acceleration in the x direction is 0 for a projectile. Let's see, our initial velocity in the x direction is, well, let's draw out the triangle really carefully. Remember, this is VB naught, this is VB naught y, this is VB naught x, and that's a similar triangle to 3, 4, 5. So we can use that to basically relate VB naught x is going to be well, let's write it down this one time, right? So the relationship here is the ratio of VB naught x to VB naught equals the same ratio over here. So that's 4/5. Okay, so we have 4/5 VB naught. Okay, and we can do that for y as well. VB naught y is going to be 3/5 of the total magnitude of that initial velocity vector. We also start at x b naught is going to be 0, right? Its y position is 100 feet upward or whatever, but its x position also starts at 0. Okay, constant acceleration is actually 0 acceleration. So we have x b of time is x b naught plus v b naught in the x direction times time plus 1/2 ax times squared. And let's see, what can we cancel out here? That one's 0. This is also 0. So xb as a function of time is 4/5 VB naught time. Okay, now we've got another expression, and now this one involves the thing that we're trying to solve for, VB naught. All right, that's what we're shooting for here. But we still don't know what the time is going to be, right? If we now said this equal to, let me get these on the screen all at once. All right, if we then now set this equal to that, that's fine, that involves that, but that's not going to tell us the time in which that happens. We need one more thing, which is like, at what time does this, is this going to happen, right? And we won't actually know that. It'll still, the time involved will have one more relationship between VB naught and the time. So now the y position of B, okay, yb of t, and I'll just write out the expression first because we have it right above us. All right, we're just going to change x to y. V b naught y times time plus 1/2 a b y times squared. And now let's come through here and say what what do all these things equal? So our acceleration for b in the y direction, that experiences gravity, minus g, which is minus 32.2 feet per second squared. VB naught y is minus 3/5 VB naught, right? Related to here, right? And I should say the negative creeps in because that actually points in the negative y coordinate direction. But it is a similar triangle, so as 3/5, the same as that fraction VB naught y over VB naught. And y b naught, the initial y position for particle B is 100. Okay, so nothing cancels out here, right? But we can combine all these to then finally get yb of time equals 100 minus 3/5 VB naught time minus 16.1 t squared, and that's 16.1 because it's half of 32.2. Okay, and we put a little dotted box. So dotted box to me in my notation means, hey, this is important, but not a final answer, not as important as what our final answer is going to be. So now if we look at this, we have one expression here that, you know, for yb. We have an expression for xb, and it involves two unknowns there. I mean, t is a variable, but we're looking for a particular time in here, right? So with these two relationships and these three, we have enough information to solve, right? So we have this expression. So we have this is like kind of what we're imposing on the system for them to strike each other at the same time along the x-axis. We have these two relationships for what x is, and now we have this third one for what y is. We just need, it's now just solving a system of two equations and two unknowns. Solve system of two equations for t star and VB naught. Okay, so xa at t star equals xb at t star, which is 10 t star. Remember, t star is an important time for which the time at which the particles meet. Okay, that's one equation. And then the other one is where ya of t star equals yb of t star, where without doing any work we know that this left-hand side here is 0. So we have 0 equals 100 minus 3/5 vb naught t star minus 16.1 t star squared. Okay, so I think what was a convenient way to go about solving this is if you look, both of these have, like, the only place VB naught shows up is when it's multiplied by t star. So I might not go through all the steps here to solve for this, but we can then write each of these VB naught t star and solve for that. This is going to be 10 t star plus t star squared 5/4. And then over here, which we can say equals to, right? So we're also solving for b naught t star by just, so we'll pull that to that side to keep everything else over here. 100 minus 16.1 t star squared, and then we'd have to multiply by the 5/3 to isolate VB naught t star. Okay, so we try to keep these separate, is that we solve for this, but these two things are then equal to each other. So now we could say these two things are equal to each other and solve for what t star is, right? And this turns into a quadratic. So let's write it like you'll have, yeah, so it's a quadratic for t star, which you solve to find t star equals 2.2237 seconds. Okay, and that's it. Now we're getting closer. Maybe I write a deeper, closer to a solid line, but that's not what we're asked, you know, what we're shooting for. We wanted to know what the VB naught, what the initial velocity for the B particle was. To do that, so we have to actually plug this back in. So plug in t star, and we could choose either one. VB naught, let's just choose this one, 5/4 10 t star plus t star squared over t star, and we get 15.28 feet per second. All right, and that division by t stars, because remember what we solved for here, this expression is for VB naught times t star, and that was just a choice to do that, right? Okay, I want to be really clear here. I know I skipped some steps. This is an equation. It's a fine expression, right? This equals that. You can solve that for t star, and that's all I did here. It's a quadratic relationship, so it does require whatever. I don't know, I have my notes here. Oh, and I can show you my own work, right? Basically, it looks like this. I just don't want to write it out. So you have this equals that. You then can solve, you know, get a quadratic equation equaling 0 and solve it using the quadratic formula. Okay. One last thing is, this is not part of the question, like we're done here, but you could ask, where do they meet? Where do A and B meet? Well, we know they meet at, right, so I'm just saying, like, we can extend this problem further. This is something that, you know, you always be ready to, like, say, okay, well, now I have a final answer. What does that say about the actual system, right? Well, we know that they meet at y equals 0, but what x location do they meet? So that would be the x star, the point of the collision. That's going to be xa of t or xb of t, but not t star, right? The important time. And so we have those relationships, right? X of A was just, actually let's do XB. XB was 4/5 V. I'm choosing this one because it involves both VB naught. And I have it right here, right? Let's see. XB of T was we solved for this relationship. XA of T has that relationship, right? So 4/5 VB naught 15.28 feet per second times T star, well, the important time 2.2237 seconds. We get 27.1825 feet. And we could check this, right? Check this with the other one, XA. 10 times 2.2237 seconds. Oh yeah, the units, there's actually 10 has some units associated with it. So 10 must have units of meter per second to get this into meters. Plus 2.2237, square that, and we also get 27.1818. So there's not, all right, we made some simplification in our, some rounding error here that's going to be the difference in the fifth decimal place, but okay. Let's get to an example here of curvilinear motion with Cartesian coordinates, and specifically a projectile where we've specified the position both x and y in time. Okay, and we're going to find many things. I'll try to fit it up here on this the screen. We'll see how we can do here. How I can do. We'll find the acceleration vector, the velocity vector, the max height, and actually we know the acceleration vector is going to be constant, right? Well, maybe we don't know that, but by looking at the position, right, these are both at most second order, right? So we should be able to, after we get comfortable doing this for a while, realize that that means that the acceleration is constant if they're at most quadratic, right? We want the velocity vector initial at the initial time, or the initial, well, yeah, it's the initial time, and it turns out to be right there. And that's because x equals 0, y equals 0 at the initial time. We want the max height, right, and then the range L. So let's see. Let's do A up here, which is the acceleration vector. And it is constant, but maybe we don't know that. We just know that the acceleration vector is some x component in the I direction, and a y component, AY is in the j hat component, is in the j hat direction. And let's do, now that we know the position here, let's get everything we could possibly know down here in like a little toolbox that we can use later on. So we'll have the position, we will have the velocities in the two directions, and we will have the accelerations. Positions, right, we know x is 86t, and y is 96t minus 4.91t squared. We know our velocity in the x direction is just x dot, or dx dt, and that is just 86. And so the acceleration is vx dot. The acceleration in the x direction is the velocity in the x direction's time derivative. And velocity in the y is y dot, which is 96 minus 9.82t. Ay is then vy, time derivative, negative 9.82. So that's a lot we can tell by specifying in Cartesian coordinates what the position is, and all the way, right? So when we come up to here, right, now we have all the information we have. This is just going to be 0 I hat minus 9.82 j hat, right, taken from this last row. And so, right, our acceleration vector is constant. It does not vary in time at just gravity, right? If we're in SI units, 9.82 meters per second squared. I think that's where that came from, right? No surprise, was probably specified to get with this true projectile. Okay, so we're on Earth, is I guess what we're saying here, right? Okay, so the next one, velocity, initial velocity vector. So let's go to our relationship for velocity. Velocity is the velocity's x component in the I hat direction and its y component in the j hat direction, which going over here, right, that's 86, not a function of time, I hat plus 96 minus 9.82 t j hat. And if we evaluate this at time 0, right, basically this term drops away. So v, let's label it like we did in the diagram, v naught. So v naught is the velocity vector at time 0. So evaluating it at time 0, we just get 86 I hat plus 96 j hat. Great. Okay, max height is the next part. See? Okay, so max height by observation. Max height is going to be when we decoupled the motion into x and y. It's one of the main ideas we're trying to get across here. At this important point in the max height location, the velocity vector is purely in the x direction. Right? There's, when we got it here, there's a y component and an x component. Now it's purely x, and then now later on it's x and now negative y components in velocity. Velocity vector is always tangent to the path. At that point, the tangent to the path is completely horizontal, so there is no y component. So max height occurs when Vy, I don't think I can fit it over there, Vy is 0, okay? So our Vy is over here, so we're imposing that 0 is 96 minus 9.82 t. We can then determine that our time to reach the max height is 9.776 seconds. Okay. Now that is not the final answer, but that is helpful because then we just go to the y location. So the max height h that we've drawn in our diagram is going to be the y location at this max height time. T equals 9.776 seconds, which is, right, 96 t, so 96 times 9.776 seconds. Well, careful with units. 96 would have a unit on it, so let's go unitless here. 9.776, that's probably good because I'm running out of space, minus 4.91 times 9.776 quantity squared. I don't know if I fit that in. Square that. .776 quantity squared, and I'm going to give up. Let's do this the old easy way here. Use a new line. 4.91 9.776 squared, and therefore our max height h is 469 when we do the calculation, 0.25 meters. Okay. And finally, this range, which now we got plenty of space. Part D we'll do down here. Right? We want to know the x location, right? So at any point here, right, this is x as a function of time, y as a function of time. Right? What we want to know is this critical point right there. What is our x location at this time, right? And it's the x location. Let's do it down here, right? We are looking for the x location. That was what L is. Find x when y of t equals, now, didn't have the entire problem drawn out here. That is given to us. I'm not making this up, right? That needs to be imposed. That's part of the problem statement. When y is negative 120 minus 120 meters. Okay? So again, we will do kind of what we did over here, where here we imposed 0 velocity, but here we're going to impose y of t. Okay, so we have 96t minus 4.91 t squared equaling negative 120. Rearrange this as a quadratic. So we have 4.91 t squared minus 96t minus 120 equals 0. Solve the quadratic, and we find this occurs at a time of 20.73 seconds. Not the final answer, but a very important result, because then our L is going to be the x value at this time 20.73 seconds, right? So if this is the time in which y takes on the value negative 120, then this is the, L is going to be the x location when we've hit the floor, or when we've dropped negative 120. By the way, the other, well, let me finish this off, right? So this is going to be 86 times 20.73, which means that L is 1,783 meters. Okay, we can make one other observation here, which is that the other solution to this time should be a negative time, and that's because the other place where this projectile crosses negative 120 is going to be down here, which is a negative time. I know it's in the negative x direction, so to go to negative 120 in y is going to be a negative x location. Well, that occurs at a negative time, right? To go to negative x, you go to negative time. And that should be the other solution to the quadratic. Okay, that's it for this one.